Okay, let's talk about ionic radii. Much like atomic radii, we can calculate the ionic radius of a cation and an anion for any element. And the premise is still the same. We first write out the electron configuration for the neutral atom. We use that to get to the electron configuration of the cation or anion. And we then group the s and p orbitals of the same energy level together. So for neutral carbon, we have the 1s with 2 electrons and the 2s2p group with 4 electrons. A carbon with a +1 charge will have 1 less electron than the neutral carbon has, and carbon with a -1 charge will have 1 more electron than neutral carbon. The shielding constant of the neutral carbon is given by the following equation. Within the same group, the valence group, right? And this analysis will be based on the valence group, by the way. In the valence group, we have 3 electrons that are shielding the fourth one with a value of 0.35 as given by Slater's table right here for the S and P electrons. And if there is a group to the left, that group shields with a constant of 0.85. Since there's 2 electrons, both of them shield by 0.85. For the cation portion, only 2 electrons in the same group shield the third one, but you still have the 2 electrons in the 1s orbital shielding with a factor of 0.85. The anion, on the other hand, has 5 electrons on the valence group, so you have 4 electrons within the same group that are shielding the fifth one with 0.35, and you have the 2 electrons in the 1s orbital shielding with 0.85. So when you multiply the corresponding numbers and add them together, you find out that the shielding constants are equal to 2.75, 2.40, and 3.10 for neutral carbon, cationic carbon, and anionic carbon respectively. The atomic number of carbon is 6, and you can find that out by looking at the periodic table. If you subtract the shielding constants from 6, this will give you the effective nuclear charge of all of the carbon species present in here. So in the case of neutral carbon, we're talking about an effective nuclear charge of 3.25. Cationic carbon has an effective nuclear charge of 3.60, and anionic carbon has an effective nuclear charge of 2.90. Alright, so now making a little bit of room right here. The atomic as well as ionic radii can be calculated using the Bohr approximation for the radius of an atom. Namely, you multiply 0.529 by the principal quantum number squared divided by the effective nuclear charge. And since we're dealing with the 2s2p group as the valence group, the principal quantum number is equal to 2. So we square that. And we divide that by the corresponding effective nuclear charge of the neutral, cationic, and anionic carbon species, respectively. And when that's done, we find out that the atomic radius of carbon is 0.651 angstroms, the cationic radius is 0.588 angstroms, and the anionic radius is 0.730 angstroms. And what this tells you is that when you remove an electron to obtain carbon plus, the size of the atom shrinks, and you get a smaller cation than the neutral species. And on the other hand, if you do accept electrons to form the anion, you actually increase the size of the atom to a larger portion. And that's probably what you've seen in books in the past. You have your diagram in which you lose the outer electron and the size of the cation is smaller than the neutral element it came from. And vice versa, if you take the neutral atom and you add an electron, the size becomes larger than what you started with. And they tend to explain it based on electron repulsions and having less electron repulsions for the cation. But as you can see right now, this is all based on the effective nuclear charge being felt by the given electrons. Looking at tables of ionic radii also provides some interesting trends in regards to the periodic table. We can see that in this table we are given the different ionic radii for all the species, and some of the elements, like if we look at the transition metals, have multiple values. And for those values, you might have noticed that there is a superscript present. The superscript represents the charge of the element. So in the case of cobalt, The 0.88 angstroms is the ionic radius of cobalt 2 plus. The 0.75 angstroms is the ionic radius of cobalt 3 plus, and the 0.67 angstroms is the ionic radius of cobalt 4 plus. So in this table, we're basically depicting all of the elements with some of the most common charges that they can attain, as well as their corresponding ionic radii. Looking from left to right on the table, it's a little bit tricky because the charges are not exactly the same, so it's not exactly an apples to apples comparison. But generally what you sort of see is that the size of the ion decreases, but it's not straight comparison because the charges are changing. Now, on the other hand, if you stick with one group and you go from top to bottom, the charges of the groups tend to be the same. So if you look at the sizes, you'll realize that the ionic sizes actually increase going from bottom to top, which is the same thing we saw for the atomic radius trend. And the same thing can be said for the chalcogen group right here. If you look at the 2 minus charge, the sizes increase for the anionic counterparts, the oxide, the sulfide, the selenide, and the telluride. But when you look at the lanthanide series, here you can actually see a really nice progression of the ionic radius. All the bold numbers represent the 3 plus state for all of these different elements. And when you look at the 3 plus state, you'll see that there's a very nice progression from 1.17 angstroms down to 1.15, 1.13, 1.12, 1.11, 1.10, 1.09, 0.08, 1.06, 1.05, 1.04, 1.3, 1.02, 1.01, and 1.00, showing a very neat decrease in ionic radius as you go from left to right. Now the transition metals, this is something I want to highlight, but not something I'm going to necessarily test you on in terms of why it's happening. But one thing to notice is that if you look at the 2 plus state, we start decreasing as we go from left to right, but at one point the ionic radius increases and then it starts decreasing again, and at one point it jumps again to higher values. So there's this double hump feature of the transition metals, and it doesn't really matter if you look at the 2 plus, the 3 plus, or even the 4 plus states. You kind of see this overall decrease in ionic radius and eventual increase in value. So there is something funky going on with transition metals. And this is kind of my cliffhanger for you guys, in case you want to take further chemistry classes, because you will learn the reasons why this happens in future chemistry classes. For now, it's kind of one to make you aware that there is some funky business going on with the transition metals. Now, in general, however, from left to right, what we tend to see is that there is a decrease in the ionic radius, and the reason why is because of the effective nuclear charge, the same reason as the atomic radii. And from top to bottom, we see an increase in the atomic radius because we're going to higher and higher energy levels. The principal quantum number increases as we go down in the series. So the same explanations for the atomic radii apply to the ionic radii. Alright, so I will stop the video at this point, and on the next video I'm going to show you an example where we utilize our ideas of Slater's rules, the Bohr approximation of the atomic radius, or in this case ionic radius, in order to come up with trends. So see you on the next video.